Hey everyone, in this video we're going to take a look at this new, exciting, and advanced new retrieval technique, which was proposed in this paper called Memwalker, which actually proposes a memory tree style retrieval augmented generation for large language models, which actually outperforms full context in some cases and in regular vector retrieval as well. So I've converted into code. We're going to review it. We're going to see how it runs. It's going to generate a tree-like summary structure from this text. We're going to take a look at this in depth, plus the code. Requirements for this is very low. All you need is just OpenAI. I'll put the link to the paper in the description. But essentially, we construct a memory tree by segmenting, splitting the text, then getting its summaries, then combining those summaries into hierarchical summaries until we have a root node of a single summary. And then we allow the large language model, by navigating through it with reasoning and taking actions and trying to find the correct segment which actually contains the answer. It's really exciting. It's actually very advanced. So let's take a look at it. I'll quickly talk about the structure and then we'll run it and see it in action. So in this tree-like structure, we have the final summary. In this case, corresponds to this one, right? The top node. Then we have the second level summary, which is a summary of three different summaries. Okay, each one of them is a direct summary of the split up version of a part of the original text. Okay, and then here we have the other summary for three of the other summaries, and that's it. So we'll try to traverse this and get the large language GPT to find the correct answer. I went ahead and deleted the JSON file, so we can run this again, see what's happening. Okay, we're initializing the memory tree. Let me zoom in. And then constructing the tree, we're getting the summarization for each. 6 nodes remaining, 2 nodes remaining. We are combining the summaries 3 by 3. I've actually created the code so that you can choose however you want to combine them. And then it actually automatically starts going into actually answering the question. But this is the memory tree that we have generated. Let me zoom out so you can see it better. So as you see, the longer your text, and your settings, for example, the chunk size and whatnot, the deeper of a memory tree you'll get. Maybe we'll test it out in the end. The way I've set up the code is that if there is no JSON tree structure exists, then it creates it. And then after that, it goes on to the navigation mode with a question. Here in this case, what is physics? So now if you run this again, it will actually go into the navigation mode, navigation initialize, navigating. It auto-generates the prompt, and then it starts asking the model. Here we go. It first gives a reason, and it says user asks the general question, what is physics? Both child nodes provide relevant information, and then it actually chooses which node it wants to go to. It wants to go to summary level 2.0, and then it goes there, and then it actually examines further summaries, chooses another level, and then at the end, once it gets to the final text, the text provides an overview of the study of physics, its complexity. However, it doesn't provide a direct definition, and this is the answer, and it is printed here. I actually got the text from the Feynman lectures posted at Caltech, so I'll put the link there as well. These lectures are really great if you're interested. Next, let's run this in debug mode and see step by step what's happening and then review the code. Before I do that, I want to mention the code will be available at my Patreon. I spend all my time, full time, researching, learning, and creating these videos. And at my Patreon, you'll have access to over 130 interesting projects and the code files. Consider me as your personal AI research assistant. If you don't have time to catch up with this stuff, I try to keep up with the most advanced, newest stuff and try to actually code it out for you, so you'll always have something to experiment with. I post a new video and project 2-3 times a week. I actually currently have over 160 projects. And if you're wondering what kind of videos I have over 200 plus free videos, my YouTube videos. You can find them at my website, www.echohive.live. You can browse through them, see their descriptions, and find the code download links. At Patreon, you can also search. For example, we are talking about retrievals, so you can search for vector and find all the VectorDB related videos. For example, it's an instant real-time search. Anyway, let's get back to the code. Let's run this and review it again. Okay, I'm going to go ahead and run it in debug mode. I have put breakpoints. You can start the debugger by clicking the debug button right here, under here, or F5. Since I placed breakpoints, we'll do line-by-line execution. Like I said, we are actually checking if the memory3.json exists. In our case, it does. Then we'll actually go ahead and load it. As you see, I'm going to go step by step right here. This one actually runs the code until the next breakpoint, and this one does step over into the next line. Because we have memory tree JSON existing, then we skip this creation of the memory tree. Actually, let me delete this. We can see that happening as well. So now I'm running it without our JSON. Then we're going to enter this loop. We're going to open the rich refinement chapter 1, and then we're going to read it, and then we're going to initiate this class. There we go. And then now we go into the class memory tree. Okay. The memory tree class represents a memory tree. The memory tree is constructed from a text using a specified model, character limit, and number of nodes to combine. Here you can specify your model for summarization, character limit for splitting. In this case, we're splitting character by character, 1,000 chunks. You can choose any number of chunks here you like. And because we are going to split and combine the nodes, here I have selected 3. What I mean is, as you see, once we get the text split into different segments, we're going to get a summary of each one, okay? But then for the next level of summarization, we're going to combine these summaries, right? Here in this case, for example, it's combining 4. In my case, it's going to be 3, but you can set it to 2 or any number you like. Then we are getting the text. As you can see, text in the debug mode, you can actually hover over your variables and you can see them in real time. Our model is going to be GPT 3.5 Turbo. Our character limit is 1,000. You can hover over and see all the variables. Also, you can see them on the left as they are being initialized. Then we're going to print initializing memory tree. Then we are going to construct the tree. And then we are going to jump onto the construct tree method because this is a class, right? We are using object-oriented programming. Construct tree constructs the memory tree. It segments the text, summarizes each segment, and builds the tree from summaries and segments. So now here we are going to use list comprehension, right, to split it up. Here we go. As you see, we are done with this line, and when we look, we have 6 split segments. If you want different style of splitting, you feel free to modify this line. And then now we are going to get summarize. We're going to call summarize for each segment. Here we go again with list comprehension. Then this is going to jump into our summarize method. This is we are implementing exponential backoff using tenacity. I guess I will put that in the requirement. I did make a mistake. You do need tenacity library so that when you can implement a decorator on the function or method that you're going to be making a call to OpenAI. So what this will do is actually wait minimum of 2 seconds, maximum of 60 seconds, multiplying the wait 2 times. Each time up to 10 times. That's called exponential backoff. Anytime we get an error back from the API. So this really allows you to overcome rate limits and errors and whatnot. Anyway, so here we're saying you're a helpful assistant. Please summarize the following text. That's it. We are using streaming responses, so we'll be able to see everything printed out in the terminal. And after that, so this the previous summaries, this one is going to call this for all the summaries. So I can just go ahead and click this, and it's going to sequentially, one by one. If I actually put a breakpoint here and run it till the next breakpoint and remove that, we'll be able to see all the text being summarized sequentially here, one after another. After it's done, it's going to return the tree, which we have built by calling the build tree. And now we have entered the build tree method. It builds the memory tree from summaries and segments. It creates a node for each summary and segment and combines nodes until only one remains, right? So again, we're going to call our node class here, and we're going to actually create keys for them too. We're going to get the summaries. We are doing list comprehension, create a node for each summary and segment. Okay, so then we are going to use this. And we do have a node class. This class represents a node in the memory tree. Each node has a key, a summary, and a list of children nodes. Okay, so if we look, well, once it's done, we'll be able to take a look. But this is just the initialization of this class. Initializes a node with a key, summary, and optionally a list of children nodes. Okay, and then this is going to complete that for us. And self.key is key, summary is summary, children is children if children is not none, right? Because each level of summaries is going to have children. Let's take a look at this. For example, the summary 9 has children, summary 7 and summary 8. Summary 7 have children, summary 1, 2, 3, and 4. Summary 1 has a child, right? Which is segment 1, but segment 1 does not have a child. This is called a leaf node. That's why we're doing a check here. If there is no children, then we assign I believe, empty dictionary, so that to indicate it's a leaf node. Anyway, we're going to go ahead and do that, and our nodes are going to be built. And one by one, I can actually click here and then go over, remove those so we can see it all done. Now, if I look at my node, I see that we have created 6 node objects. That's good. And then we are still continuing to build the tree. We are checking if we have more than one node, because we do want to create the tree until we no longer have a node, right? When we reach the root node. So this is going to do that. While nodes are larger than 1, then we are actually printing. See, grouping nodes, 6 nodes remaining. Then we have another group the nodes. See, group nodes is here. We have grouped these 2. And then now we are getting recursive summarization, right? So here we are calling the summarize again because we're grouping the nodes. If we go back to the chart again, essentially we first summarize the split text. Now we are combining the summaries, right? Okay, now we're going to the next level. And we are now grouping the nodes, 2 nodes remaining. So this is our final step. I believe we're going to get the summaries. Okay, here we go. Yeah, should be it. Yeah, and we're done. Now we are going to return our nodes. So this was the final summary. We return those. And then now we're going to call the construct3 method, which we are done with that, I mean. And then now we're going to print memory3 constructed. And then we are going to call the save3 to file, which is just going to open it. And since this is a dictionary, we're going to dump it using JSON right here. Let's indent 4. There's comments for each one of the lines. Okay, and then here we call the toDict function, converts the node and its children to dictionary. If the children are nodes, it recursively converts them to dictionaries as well. If the children are nodes, we're going to run this, convert them to dictionary recursively. Here we go. Doing that. If the children are not nodes, because eventually we're going to run into that situation, right? When we run into the end leaf nodes, so then we just return, right? Our dictionary, and we repeat this until it's done. And it just runs a few times, and now we're going to create a new JSON object, dump it, and 3 save the file. Now if we go to our memory3, so this top summary, okay, is like the summary 9, and then the second this one, and this one is like summary 7 and summary 8 here, and then it's underlying nodes like this one, and this one is like the direct summaries of the split text, and underneath them we have the actual text right there. Okay, and as you can see, each time we have children, but when we are actually at the very bottom, then we no longer have children because this is our leaf node, as you can see. So this pretty much concludes the memory3 construction. Now we just print the final summary, right? The root summary. If you look, this text introduces 2 here, and this is the one that we have right at the very top. Just to iterate the point, this is our top summary, right? Summary of all the summaries. Now our next step is going to be loading the tree. If we had this tree.json, then we wouldn't create it again. So next we are going to go into the navigation mode, and then we are going to be answering the question, what is physics? But before we continue, I just want to again mention that you can browse all my videos at my website, www.echohive.live. And if you feel generous and are interested in interesting and advanced projects, please consider becoming a patron. I appreciate it very much. Links will be in the description. We also have a vibrant Discord community. Link will be in the description for that as well, if you'd like to join us and chat with us about large language models. Anyway, so now we are examining the navigation part. So we do have a class navigation. And before I continue real quick, see, our first class is the node class, which we have talked about. Second class is the memory tree class. Okay, the third one is the navigation class. So we are here right now. This class represents the navigation through the memory tree. The navigation is initialized with a tree and a model and can navigate the tree in response to a query. So we're going to get GPT to actually reason and navigate it automatically. So here we go. We print initializing navigation. We are actually defining our tree here. What tree are we navigating, right? Here we go. We have grabbed our tree. And we are defining our model. So we are using 3.5 for summarization and GPT-4 for navigation. Now we say navigation is initialized. Now we're asking the question, what is physics? Okay. And now we go into the navigate method, navigates the memory tree in response to query, generates a prompt. So we are auto-generating a prompt with quite a lot of dynamism going on. We ask the model and then we parse the responses. We are not using function calling here. So that's cool. I mean, it makes it easier, I guess, but it works well in my experience, and either goes to a child node, reverts back to a parent node, or returns an answer. So what's going to happen is GPT is going to look at the summary, which is going to contain these two summaries. Okay. So it's going to decide, okay, where is the likely answer, right? So it's going to decide, oh, the likely answer is here. So it's going to go here. Okay. And then it's going to decide, well, the likely answer is maybe in summary 2. So it's going to go there. So if it decides that, oh no, the answer is not here, it can back off back to this node and then go back down to the summary 3, for example. And then from there, find the actual text and try to answer the question. So that's what's going to happen here. So we are starting our root node, I believe. Yep, there we go. And then while we have children, we are going to generate the prompt. Because while we have children, that means we haven't reached the leaf node. And then we are going into the generate prompt right here using the node and the query. Our query is, what is physics? Generate prompt generates a prompt for the model based on the current node query and the memory of visited nodes. So we are going to be keeping track of the visited nodes. If the node is a leaf node, the prompt asks the model to reason about whether it can answer the query. If the node is not a leaf node, the prompt asks the model to reason about which child node to go to the next, or whether to revert back to the parent node. So here we grab the visited keys. Currently, it's empty because we haven't visited any nodes yet, right? So if we check, if we have children node, then we are going to use this prompt. If not, we're going to use this. So, sorry, we are checking if this is a leaf node because we are checking for 2 conditions. So we will use this at the very end, right? So we skipped this and we went to here. So now we are going to get the children summaries using list comprehension. If we hover over this, so see we get the summary level 2.0 and summary level 2.1. If we go back to our memory tree, say we are grabbing this and we are grabbing this, which is essentially equating to here summary 7 and summary 8. So we are going to construct the prompt. We are going to say you're a helpful assistant given the query. So we are giving it the question. The following summaries of the child nodes, the children's summaries, we are actually inserting, right, the keys for those as well. So it knows which summary. And the keys of the visited nodes. So we are also giving it which nodes it had visited, currently none. Please reason about which child node to go to next or whether to revert to the parent node. After reasoning, please state reason, followed by your reasoning and your action in the format of action. Always start your action with action, so right. And now we're going to print asking the model. Then we are going to go into ask the model. So this is just this. We have already constructed our prompt. We're only using a system prompt with streaming. That's it. So we're just going to make a call. Okay, that's it. So let's make our call. Here we are reasoning. The user asks a very general question about what physics is. Both child nodes provide relevant information and the roles. However, summary level 2.0 provides a more general overview. So therefore, it picks action summary level 2.0, right? So what do we do next, right? We go into parse response because we need to get the action. Parse the response from the model. If the response contains an answer, it extracts the answer. If the response contains an action, it parses that action, right? And we want to use that command. So we check if there's an answer, not yet. So we skip that. We look at if the content contains an action equals, which it does, right? Then we go in and we check for summary level because this is how our keys are named. And then we split it and take the last items after the dash. And then we return that action. And if the result type is action, then we say the result value is -1. If this is true, then we're going to revert back to the node, but it is not. We are actually going to the child node. 0 in this case, because it had picked the first one, right? And here we go. We are just getting that node, grabbing that node. And then we are again now generating the prompt. Now we are generating the visited keys. See, we have visited summary level 2.0. Again, we are getting the children summaries. This time summary level 1.0. And now we have three different summaries. If you take a look, summary 1.0, summary 1.1, and summary 1.2, because now we are going deeper, right, into the keys. We have selected this one. Now we are looking at this summary, and then this summary. Again, we are constructing the prompt, and now we are again asking. And then the model is going to reason. The user asks the general question, summary provides. So it's taking a look and it decides the summary level 1.0 might contain the answer. We again parse the response. Okay. Take a look and go into the child node. Again, now we are going to generate a response again. We take a look at our visited keys. Here we go. There might be an issue here. I'm not entirely sure if this is being done correctly. Feel free to debug it. I mean, I believe most everything is available for you to actually make this better and use it in your use case. So this time we are actually we no longer have any more nodes, right? We are at the final leaf node. So that's why now we're going to craft this prompt. You're a helpful assistant given the query. The following text. And the key of the visited nodes, please reason about whether you can answer the question. After reasoning, please state reason, and if you can answer the query. So we want to answer the best it can. Right now, we're going to ask the model. Okay. Again, we are making a call to GPT. Let's see what it does. It says the text provides a general overview of what studying physics entails. But it does not, but it does not define what physics is. Therefore, I cannot directly answer the query based on the provided text. And it says text does not provide a definition of physics. And then now we parse this. And now we find an answer. Now we go into this condition. We are going to extract that answer and return it. Okay. And then now our navigation is complete. We print that and return the result value, print it, and then we're done. Okay. This is it. I mean, this is just lovely. It works. There is a memory implementation. So in the original paper, if you read the paper, there is actually examples of how the prompt works, and there is actually some kind of working memory. I haven't implemented this because I wanted to save on some tokens. You can definitely implement it. There is an example of it here that we are using memory right here, self.memory, but we are not actually applying it. Make sure that if this works correctly, I mean, run it and debug it for yourself. But we are using the visited keys, which might not be generated correctly. Take a look at that too, because we are popping it somewhere over here, right here. So examine the code. You know, this works great, but it might need some improvements, especially to adapt it to your use case. So in general, right, we have a node class, and then we have a way to convert these to dictionaries. We have the memory tree. Which generates the memory tree, constructs it, and then saves it to a tree and to a JSON file. We have a summarize method to summarize each one of these. Here is our save to tree, and we have the navigation initialization, the navigate method, generate prompt, which dynamically generates whichever prompt is needed. And we have this ask model call to GPT-4, and then we have the parse response method, which parses the actions after the GPT has reasoned about all that. And this is the general loop of our program. Like I said, this paper is very interesting. Take a look at it, read it. I'll put the link in the description. Also, take a look at the Richard Feynman's physics lectures. These are great. Examine the code, make it work for your use case. I believe this can be very useful if you don't want to use vector database. One of the limitations that the paper mentions is that this might not be appropriate for very, very long text. So you can read and find the necessary things. But some of the things I learned while reading this was the fact that the evaluation, right? So they compared it and they found that in a lot of cases, it actually beats keep left style of full context. So keep left and keep right. I realized these are two things I didn't know before. It's almost like if your text is too long, but you still want to use full context, like copy paste right into the context window, whether if you're going to keep the certain amount of tokens, let's say 5,000 tokens from the beginning of the text or from the end of the text. And this middle bar represents that the beginning of the text, right? And then the light green blue represents the full context from the truncated by keeping the end of the text. So as you can see, Memwalker beats full context quite handily, except in this particular case. And it also turns out in these two examples, keeping the bottom half of the text actually turns out to give better results here in these cases, but not here. So that was interesting to look at. Okay, this is like a short paper, so they also compare different kind of token segmentation, right? Here, I guess they had better results with 1,000 token segments. In this case, we're not using tokens. Okay, these are character limits, but you can assume about four characters being a token. So if you wanted to simulate 1,000 tokens, you probably want to set this to 4,000, give or take. Okay, if you don't want to deal with tick token, that is. So please let me know what you think of this. Like I said, the code files will be available at Patreon. Link will be in the description. If you like the content, please give it a thumbs up and subscribe for future videos. Let me know what you think in the comments or at Discord. And see you in the next video. Thank you for watching.